Good morning, everybody. Okay, today we will go ahead with like formulation of the finite element shape functions and all for different kind of elements and all. Okay, so but before that, so yesterday during tutorial there was a question about we have like from a strong form we get the weak form, and similarly from weak form, just to show that both are equivalent, so we can also go from here, that is the weak form, to a strong form. We can prove it basically. So looking at this, the example we had, and we have example of this. So u0 equal to 0, let us say, and EA du over dx equal to f naught. That was the that were the boundary conditions, and our strong form, we know that this is du over dx, EA du over dx plus bx equal to 0. And if you convert that into a weak formulation, then you know that this becomes WEA du over dx, and then it becomes L to 0 minus 0 to L EA dw over dx du over dx, right? Dx plus 0 to L WB dx equal to 0, right? So we get that. Okay, this is, let us say you went ahead, you put all those values. So if this is the form of the weak formulation, if you put this back, this one, if you start converting this into a strong form, you will integrate this as integration as parts, and then you will again get this term, and then you will get this term, so, and then you do whatever we have done earlier. Only thing is about the question was about this about the boundary condition. How do you get back the boundary conditions? Okay, so if you put these values first, so here we have WL, and then we have this value, and then you have W0 minus W0. So W0 will be 0 because U0 is 0, so W0 will be equal to 0. And so that really means here we can have WL times EA du over dx at f equal to L. So actually the x equal to L is f naught. So we get WL times f naught, right? And then minus W0. So W0 is 0, so that term will not be there. And then we have the other things, right? Then you have 0 to L, and rest will be this one. This. Okay, then what happens? Like, okay, so the final weak form will be, in this case, WL times f naught minus 0 to L, minus 0 to EA, then you have dw over dx, u du over dx, plus 0 to L w dx equal to 0, right? So we have this final formulation, and where we also, the problem is find ux such that u0 equal to 0, and right. So you have for all w's, yeah, right, for all w with w 0 equal to 0 is given. So this is the full statement of the big formulation. Find ux such that u at 0 equal to 0, and this is equal to 0 for all w with w 0 equal to 0. Yeah. So this is the formulation, which is the full statement for the weak form. Okay, now we have to now go back from here to the strong form. So we will do integration by parts now. So WL times F naught minus, and we will have this integration by parts means we have, so this guy you put here, so we will have W, right, W EA du over dx L0 minus 0 to L W EA, or not EA, but we will have, before that we will have d over dx EA du over dx. We will have that plus 0 to L W bx dx equal to 0. So this, you know that this becomes minus plus, and this both will be together, right? So, or if you look at this, if you look at this, now in the weak form, this is given that W at 0 equal to 0. So what we get here, WL times F naught minus WL EA du over dx. So we get this plus 0 to L W d over dx EA du over dx plus B dx. Yeah, that's equal to 0. So I will combine this and this, minus becomes plus, so combine them together, and this is given that W0 equal to 0, so you put that value, W0 is 0, so what we are left with this one, right? Now it has both the things, so if you expand that further, then what do you get? You get W at L, then F naught, right, minus, and then you have EA du over dx at x equal to L, right, and plus you have 0 to L W d over dx EA du over dx plus bx dx equal to 0. So now from here we have to actually find out, yeah, this here we have finally we have to get in this form, right? This is the idea, to get this form, right? Okay. Now this is up to us to remember that W is arbitrary, right? W is arbitrary, so we can choose W to suit us. So you can choose W equal to phi x, yeah, multiplied by d over dx, EA du over dx plus bx, right? And also you can, since you have phi x, you still have some liberty. You can still give it some value. And what value? Remember that it has to follow W0 is equal to 0. So that liberty it should have. And how it will get? It will get from the, because you have phi x will take care of, because phi x could be such a way that helps W in getting these values. We can also have another condition, because W is arbitrary. We can have another condition that WL is also equal to 1. Yeah, we can have that, right? Okay, now if you put this value here, then what happens? This makes it so if you put these additional condition, these conditions, if you put, then we have WL equal to 1. So we have F, for example, so this F naught minus EA du over dx at x equal to L plus 0 to L, yeah, and then you have phi x greater than 0 is given, yeah, and then you have the whole thing here, d over dx EA d over dx square plus b square dx equal to 0. Yeah. Fine. So yeah, what do we get in this case? If it is always 0, if that makes equal to 0, we know that this term is 0, right? This sorry, a square, so it's positive. This phi x this is positive, right? Okay, so that means that we can have at least one possibility in which we have F naught minus EA du over dx at x equal to L equal to 0 and 0 to L this phi x d over dx EA du over dx plus b square dx equal to 0. Yeah. So this term, if we have okay, so here I think you should put WL as well, and this is true for regardless of which W you take, you know. So this regardless of this arbitrary, regardless of which W you take, it's always true, right? So that really means that this has to be this equal to this and this equal to this. Yeah, so this is also arbitrary. Yeah, so the WL equal to 1 while by example, it is just an example. Yeah, so but this W is arbitrary, so here W can have any value, and regardless of which W you have, this has to be true. That only when this also equal to 0, the whole thing equal to 0, this also is equal to 0, and this really means that from first one you get the boundary condition EA du over dx x equal to L equal to F naught. Yeah, so this is the natural boundary condition you get from there, and this automatically get that also d over dx ea du over dx, right, plus bx equal to 0. This also will be. And to begin with, u 0 equal to 0 has to be there, because in both the cases, in weak foundation also you say find ux such that u 0 equal to 0. So this will be there. Is it fine? Aditi, did you get it?
Sir, actually, in there, what they had done is they had taken WL equals 0 for the first proving well, when they tried to prove the strong form. And after that, later they have taken such a function which gives WL equals 1. Like they have done something like this. And sir, I was not able to understand that how can they change W function for W? Like
No, no,
initially they
no.
had.
So no, this should not be there. You check, the problem will be different. Yeah, their problem may be at w zero equal to something, zero, wl equal to one. There where is u given?
Uh,
So the problem may be
yes, sir.
different
Yes, sir.
from,
Yes, sir. Yes, sir.
yeah, the problem may be different from what we solved. Okay,
Yes, sir.
got it. Yeah. So you check that. Okay, so it should not be arbitrary like that. Yeah.
Okay, okay.
Yeah, you just check that. Yeah, so it cannot be, if it says w zero equal to 0, so it will be w zero at equal to 0 only. Yeah, and wl is arbitrary, it can be any value, so it's saying just, for example, wl equal to 1. Yeah, so it goes like that. Yeah.
Yes, sir.
Sir,
It.
Yeah.
sir, in the book, in chapter 3, when they derive the strong form for a 1D elasticity problem, they
Mhm.
take W at L is equal to 0. They assume the other boundary condition as at x is equal to 0, E du by dx is equal to the traction force, the negative minus T.
Yeah, it
And
depends on the problem, no?
and in the
So
problem, U is given at L, and the solution they find u the function of x.
yeah, it can be like that also. So see, our problem is like this. Their problem is like this, right? This is, you in the class, in the lectures. This is in the book. So which is the same thing. Yeah, it's the same thing. So here you have u zero equal to 0. Here u l equal to 0. Right? Got
Uh,
it?
but still, sir, actually, they have changed something. Like, firstly, they have said that this is they have given phi x.
Hmm.
So, is it like they have defined wx equals to phi x and the same complete form, and then they have derived that this strong form comes.
Hmm.
Uh,
Sure.
but after that, they have changed the w, and what they have done is they have said that now we know that the strong form is already zero, so the other terms becomes zero now. They have used a different w and put this strong form equals zero there, and then proved
Okay,
the.
so one thing, like, did you understand what we did today? Did you get this one? Do you agree with what we did today in the class?
Yes, sir, but like how, like you said that there's a possibility, so they cannot be negative. Like I didn't
Which
catch that.
which one?
Like you said that now WL is 1 here, and
No, no, no. WL equal to 1. I'm saying this is a one example I'm saying. Okay. In fact, I haven't even used it.
yes, sir. So how did you say that is zero and this is zero? I mean, like
No, 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 this is
possibility.
no, no, this is not possibility. This will be 0 equal to 0. Why? Because this is, we have two terms, right? We have two terms. So one terms is phi x always is greater than 0. Right?
Yes, sir. Then how do we know that the first WL into F naught minus EA du by dx is not negative?
Because WL is arbitrary, right? So we can have like regardless of what W you take, it's always 0. So it's only possible when individually both are 0. Right?
Okay.
Individually, in that case, individually it has to be equal to 0, no?
Sir, and F naught minus EA du by dx, can't it be negative?
No, yes, it can be negative, but you see, I think here,
So, okay,
regardless of
that is positive. No, 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 no. But still there
no,
is
no,
a
no,
problem.
no, it's fine. But what I'm saying, regardless of what you take, it's so if it is negative, suppose you choose WL to be negative, then what happens? This up to you, no? Regardless of what
Okay.
W you take, this has to hold. That really
Okay.
means if it is positive, for example, and if this is positive you are taking, that means it has to 0. Now, if it is coming negative, if you take this to be negative, then it has. So it's
Both
up to you,
positive and
no?
zero.
Yeah. So
Okay.
W has endless possibilities, and it's up to you. Regardless of which W you take, this statement has to hold true.
And phi x, we can take anything depending on what is coming that side. Okay, sir.
Yes, yes. That's why. You got it?
Yes, sir.
So see here we will not go into so much mathematics, So purposefully we have a lot more things to do. The idea here is to it is not even important to say that weak form and strong form are equivalent. Actually, they are not equivalent. Actually, it's not equivalent because solutions will be different. It is just you do some few things, manipulate a bit. I would say manipulation. Basically, you approach from weak formulation to you want to go to a strong formulation. We know that solutions are different, so they are different equations to begin with, right? It's actually they are not equivalent, but they correspond to each other. You can say the one-to-one relationship. For one strong formulation, there will be a unique weak formulation, and vice versa. Yeah. So that much is true, but both are not the same thing. We will not even like use that later on, that both has to be equivalent and like that. So we don't have to even prove that this formulation has to go. You have to obtain a corresponding strong formulation. Yeah. This is to know that how you are changing from one which has a strong stringent requirements to one form where requirement is less. From a strong form where there may be a solution which will be unique and it will be difficult, to a weak formulation where solution may be many solutions. It's not just one, but many solutions it can admit. So that gives us flexibility to choose our own solution. So so even if like you see like in you think that does not make sense, well, it is not important, that I can tell you. So we will not use much. We are not going much into the mathematics. We will look at the how to solve the problem. So from once we get from the strong form to weak formulation, in weak formulation we will do put different what you call it, trial function, right? So this is trial functions which is important. We have to look at as you said, like what kind of trial functions is possible. Let us say in some problem, if solution is this is the actual solution. Let us say this is the actual solution, and what we are aiming for is something like this. So we want a solution. Let us say we are making linear, piecewise linear as a solution we are hoping that we can get this kind of solution, and for that means what? We want to match just a few places. You want to match at, let's say, equal to 1, node number 1, then this becomes U2, this U3, and this U4. So these are where the nodes are, like node number 1, 2, 3, 4. So we want to match that. Yeah, so this is our solution that we want, and approximate solution. For that, our trial function we write in a particular way, right? This is actually what we have. So basically, ux, if this is the x which is going, then accordingly we can write the like ux equal to, we have write accordingly, and u1 plus, right? How do you write? Even x, let us say this is L1, from here L1, this is L2, L3. So you can write, either you can write U1 plus U2 minus U1 over L1 times X, right? Just linear interpolation, right? So this will be for X 0 to L1, right? Equal to, you can interpolate U2 plus U3 minus U2 over L2, right? X minus L1. This is true for X, L2, L1. L1 plus L2. L1, L1, right? Equal to U3 plus U4 minus U3 over X minus L1 minus L1. Right? This is true for X, L1 plus 3. Right? So this is this
So your voice is breaking.
okay, guys. And can you hear now?
No, sir.
No. The problem on camera. Can you hear me now, guys? Can you hear me now?
Yes, sir.
You are with me?
So your presentation is not visible. I don't know if others can see.
Yeah, just a minute. Okay, sorry guys. So hope you are hearing my voice now.
Yes, sir.
Yeah. Okay. So I was saying that a solution, actual solution could be something like this, smooth, but you want a solution which is approximate, which could be a linear, piecewise linear solution, something like this one. So let us say u1, u2, u3, and u4 are the actual values of displacements at x equal to L, x equal to L1 plus L2, x equal to L1 plus L2 plus L3. And then you want the solution to be something like this one, u1 plus u2 minus like this. So basically what that is, this is something like piecewise line only, and it has continuity here because both of them will have same values here. So, and this you also you can write something like this. You can write as ux equal to you can say n1. Let us say this is node number element number 1, n1x u1 plus n2 x u2, right? That is for element number 1. So as far as x is within element number 1, you have this one, or it will be element number 2 x u2 plus element number 2, sorry, it should be 1 2 2x u3 for element number 2. When x is within element number 1, you can say when for, okay, v is equal to n31x u3 plus n3 2x u4 for element number 3. What is the meaning of element number 1 to 3 saying? It is the same as saying that 0 x from L1 0, meaning that this is L1 x, L1 plus L2, here L1 plus L2 less than equal to x less than L1 plus L2 plus L3. Yeah. So that really means if that is the case, whatever we wrote here, this is same as this. When you have these are linear functions, right? What you call the shape function. And how will this look like? This will look like if you plot same x, like if you have x here, right? You have x equal to 0. Let's say this is x equal to L1, x equal to L2, x equal to L3. Sorry, x equal to L1. This L1 plus L2. This is L1 plus L2 plus L3. So that you have L1 here, you have L2 here, this is L3 here, right? So then how will this ends look like? It will be, let us say this is 1. So here you have 1, here you have like this. So the value, this will be nothing but N1, 1. Okay, this will be N1, 2, right? Okay, now next. Here, this will be N2, 1, right? This will be N2, 2. Similarly, it goes here to here, here to here. And this is N3, 1, right? And this is N3, 2. So these are the equations. I mean, how they look like basically. What is how they look like? So since we are writing this way, so let us say ux for element number 3. Within the element number 3, they vary like this. You know, so when x is within x is L1 plus L2 but less than L1 plus L2 plus L3, that really means x is somewhere here. And here it is saying that u3 minus n1 3, n3 1 and u4 multiplied by n3 2. So that really means u3 multiplied by this plus u4 multiplied by this. So automatically this interpolates between u3 and u4. Got it? So here our formulation of the trial function itself is such a way that it automatically, you know, scales between, I mean, the interpolates between the nodal displacements. You can also change this as like this, you know, so you can write, for example, you can have n, let us say, let's call n3 1 x. How will you write? This will be simply 1 minus, right? 1 minus, you will have x minus L1 minus L2 divided by L3. Yeah, this is how you will write, because you see, if x equal to L1 plus L2 plus L3, then you have L3 and then you have L3. So 1 minus 1 becomes 0. So this is how it will be. When x equal to L1 plus L2, you write L1 plus L2, then this becomes 0. So you have 1, right? So this is how N31 is, right? Similarly, N32x will be simply x minus L1 minus L2 over L3. Now you can transform the axis. Let's call this is, let's call it xi. Okay, so something like this is equal to x minus L1 minus L2. You define like that, right? So you can change it, and if that is the case, this n13x becomes 1 minus, and you have xi here, this becomes xi, so simply xi divided by L3. Yeah, so you have converted n1 xi becomes 1 minus xi over L3, 3, N3 2 xi becomes xi over L3. Now your that means your u x is equal to u3 1 minus xi over L3 plus u4 xi over L3 for xi 0 less than L3, or that really means you are talking about you convert, that means x L1 plus L2 plus L3, and here you have L1 plus L2. So finally you can convert this way, so that what I mean to say is individually you can work on, universally you can tell that N1 is equal to 1 minus x over L, N2 is equal to x over L, and you can formulate the problem. So you don't have to go individually and find out the stiffness matrix. You don't have to do. The stiffness matrix can be done just assuming, so like if you have element number 3 in this case, let us say, right? So you can just take that element number 3, either actually this is like this, x equal to L1 plus L2, and here x equal to L1 plus L2 plus L3, and then you don't have to do like this. You just take this and you say this is x equal to 0, x equal to L3, and you have N1 equal to 1 minus x over L3, N2 is equal to x over L3, and you do all the analysis, you can get the KE, meaning that the element stiffness matrix. Yeah. So we are doing this just one time, just to see the broad picture, how it is connected, why we are not doing them individually. We just assume we take one element and we take the local coordinate system and we work with this. Only when you have bx, like let us say you have, in this problem you have bx also given, and you have element number 1, x equal to 0, x equal to L1, x equal to L2, x equal to L3. Now if bx is given equal to x square, let us say, then you have to be careful there, so because when you change the axis, make sure that bx is also converted into that. So we will come back to that later. Okay, so meaning that what for n, we have to only find out the stiffness matrix for the individual elements, and for that we can go local. So this is the bottom line. So if we have several elements, yeah, and let us say for this eth element, we have to find out if Le is there, and if you have to find out the stiffness matrix, we will draw here the eth element, length Le, and for that shape function will be Ne1 x, and where x will be the local, or we can also write zeta xi, Ne xi equal to 1 minus xi over Le, N2E xi is equal to xi over Le, and we do the K is Kij equal to, for example, Ea d N1 over dx, sorry, dni over dx, dnj over dx 0 to L. Not x, but you will have xi here and this. So you have to work in the local coordinate system, local coordinate, local to the element only. So and that makes life simple, because in local you can write like this. Yeah, and this is how you can find out the stiffness matrix. Now we will look at the shape functions has some property. And what property we have? We will see that for this, we if you have this element like this one, you have u1 and u2, let us say, right? Within that, ux equal to n1 x u1 plus n2 x u2, or you can take xi as well, doesn't matter, but we are looking at the property. So this done, we are done with this. We are looking at the different aspect, and you know that ux1 means if x equal to x1, x equal to x2, right? So node 1, node 2, node 1 is at x equal to x1, node 2 at x equal to x2, let us say. So ux1 has to be equal to u1, right? It is possible only when n1 x1 equal to 1 and n2 x2 equal to 0, right? Okay, and similarly ux2 is equal to u2 is equal to n1 x2 u1 plus n2 x2 u2. That really means n1 x2 equal to 0 and n2 x2 equal to 0. So we have these values. Which values? We have n1 x1 equal to 1, n2 x1 equal to 0, and then we have n1 x2 is equal to 0. Sorry, here it should be 1, and n2 x2 equal to 1. So that really means n1 and n2 can be what? n1 and n2 can be linear. That means we can say, let us say n1 x is equal to, you can also write that way, is equal to alpha 1 plus beta 1 x, let us say, and n2 x equal to alpha 2 beta 2 x, let us say. Because so that means if you look at this, we have just two equations, right? That means we can, at the maximum, we can have two coefficients to find out. So if that is the thing, if x1 equal to, if n1 x1 equal to 1 and n1 x2 equal to 0, that really means we have two equations, and hence we can have only two coefficients, because two equations will find out the two coefficients. Hence it can be a linear, right? And similarly, you can also have, instead of x1, you can have 0. So you can have x1 equal to 0, x2 equal to L. So that makes life simple. And that really means what? You can actually find out now how the value looks like. So n1 0 is equal to 1 is equal to alpha 1 plus beta times 0 is alpha 1. Alpha 1 equal to 1. n1 L is equal to 0. That really means alpha 1 plus beta 1 times L is equal to 0. That really means beta is equal to, what do we get? Beta we get that
minus 1 by L.
Minus 1 by L, correct. So alpha 1 equal to 1 plus beta 1 times L is equal to 0, and beta 1 equal to minus 1 over L, and hence n1x is given by alpha 1, which is 1, and minus 1 over L, which is beta times x. So 1 minus x over L. Similarly, you can find out for n2. What do we have? n2 0 equal to 0, right? And that really means alpha 2 plus beta 2 times 0 is equal to 0. And that makes it alpha 2 equal to 0. N2 1 N2 L equal to 1. Alpha 2 plus beta 2 times L is equal to 1. That makes it beta 2 over 1 over L. And hence N2x is equal to alpha 2, which is 0, plus beta 2, which is 1 over L times x. That makes x over L. So we get N1x equal to 1 minus x over L, and N2x equal to x over L. What you see here, N1 plus N2 is equal to 1 minus x over L plus x over L, that equal to 1. So also you see that N1x plus N2x is also equal to 1. So what you are seeing, the property here. Property is if you sum them together, you get 1. Okay, so before we leave, I just want to just think about it. Tomorrow we will do it. That if you have 3 noded elements, then how will you write U? So this is U1, this is U2, this is U3. Yeah, and accordingly, if you have 3, you will have what? Let us say you have Ux is N1 U1 plus N2 U2 plus N3 U3. And that really means what? How many equations can you get? So that really means possible N1 at element x equal to, let's say you call it x equal to minus L, x equal to 0, x equal to L. So that really means what? Sorry. N1 minus L has to equal to 1, N2 at 0 equal to 0, N3 at 0 equal to, N1 at 0, N1 at L is equal to 0. N1 has to be 1 here and it has to be 0 other places. Why? Because you have to, N1 is multiplied by U1. So N1 has to be 1 here so that U becomes U1. Yeah. Similarly, N2 has to be 1 here and N3 has to be 1 here and 0 elsewhere. So if you have 3 equations, how many coefficients can you solve? 3 coefficients. And that's why N1x now will be alpha 1 plus beta 1x plus gamma 1 x squared. So 3 noded elements will have quadratic interpolation function. Yeah, and so on. Yeah?
Sir, the difference between the nodes is always same, like you have taken a minus L0 and L. Like L is the length.
It's up to you how you formulate, but typically it is exactly in the middle it will have, because it makes life easier. Right?
Okay.
Sir?
Yeah.
Sir, my question would look like very absurd. Okay? But the thing is, like, why we are using this strong form and weak form? Like, what we used to do is making the stiffness matrix, assembling them, and solving our equations. But what is the benefit of this strong form and weak form? I want to know this, actually.
Okay. A strong form gives you solution which are exact but difficult to solve. Okay.
So
Problem.
can we have an example of that? How we are getting those difficult solutions and like easy solutions from the weak form and very difficult solutions from the strong form?
Your example could be, let us say you want to solve a problem. I gave you a problem. Can you solve it? You tell me how to solve it. Okay. Here we have some body force dx equal to log of 1 plus x square, e to the multiplied by e to the power beta x. So this is your body function, body force. Okay, and this is the equation. d over dx, and E is also varying, let us say, and A of course is varying du over dx plus bx equal to 0. Can you integrate it? Very difficult to integrate. If you take bx that side and you have this, and then you have to integrate, let us say you have even more difficult thing, then even if you integrate this one, then you have to divide it by ex and ax. Ex, let us say, is equal to sine of beta x, and ax equal to we can have some even other function tan alpha x. Yeah.
Yes, sir. Sir,
Now you tell me.
can we do one thing like decrease the size of our element we are taking and consider them as a linear element like
Yeah,
what we.
yeah. That's what you do.
Yes, sir. So that is I think I mean
Hmm?
might not pose a like it is actually conceptually different for a strong form and weak form, but it will be actually if we decrease the size of our element, then it will be easier to go with this approach than going with this strong form and weak form and doing all these extra things from that.
Decrease the size you are saying and calculate, but how many? How many will you take?
So we can do it by by the help of like software systems and all those.
How many you do? Just you try to do. It will be mind-boggling. It is very difficult to do. You are saying that in that case you will just divide this into a small things that you will do. Now you tell me how will you calculate the force to begin with? You agreed, but you have to compose also the force vector. How will you do it? I give you a simple example. You tell me if you have a node here and a node here, okay, and in middle you have a force, not middle, but somewhere 1/4 of this. Let us say L over 4, 3 L over 4. Here you have a force F naught, and you happen to have one node here and one node here. Now, finally, this force has to be transferred, has to appear in the force vector. How will you do that?
So we can create one more node at the point where
No, see, I mean, and if you have an infinite number of those forces, then what will you do?
okay, okay, okay.
Yeah.
I'm getting the point.
When we um, move ahead, we will see. So we are taking simple examples. It doesn't mean that in real life examples are the simple one. No. Okay. Real life examples could be more difficult one.
Yes, sir.
Okay.
Yes.
But motivation here is to admit infinite. That's why we formulate into weak solution, right? So we do finite element when we are unable to solve using the analytical methods. Otherwise, we don't apply it,
Yes, sir. Yes,
right?
that is.
Yeah. So it's not that I draw one bar here, so for that you need to apply. No, this is the solution is known. But taking simple examples so that you easy to understand. Yeah.
Yes, sir. Sir, I was having one more doubt. Can we generalize this statement like what I'm saying that we are getting an exact solution by the strong form and by an exact solution
True.
and we are getting a weak solution in the weak form in the form of a function of x or a length whatever we are taking we are getting it as a function of x and that will be same as the solution of the strong form at the nodal points only.
Yeah. True.
Okay. Okay, sir.
Yeah.
That
It
was
is like that one day. Yeah. Any other question, guys? Yeah. Okay. The weak form is important because you know exactly how to find out the stiffness matrix, how to find out the force vector, and how the equation will be Ku equal to F. Weak formulation is the one that gives you exactly Ku equal to F, automatically puts things at right places. So if you don't do weak formulation, you will not even know where the F will appear. I mean, which all components will be there, how to calculate the force vector, that we will not know. Yeah. And this is what we are going to do. Yeah. So tomorrow we will learn, even we go further. We wanted to just make connections so far. So far that's why, because of these difficulties, I'm trying to make connections. So that's why in chapter 2 we use direct method. Chapter 3 we have two different kind of methods: Rees method, Galerkin method, and then finally we are trying to find out why we learned those, and what different we are doing now. Our just the test function is different now. Earlier we took just one function, now it is a piecewise function. Yeah, and from there we are going forward. Okay, so we will what we will do tomorrow, we will look at the three noded element as well, and we compare with the two noded element, and we go from there. Okay guys, see you tomorrow then.
Thank you, sir.
Thank you, sir.